Hello everyone, welcome to another edition of Subject Math. Our topic today is gravitational field. Gravitational field is the region of space where the influence of the gravitational force is felt. What do I mean by that? The region of space where the influence of a gravitational force is felt, okay? I'm just going to cite an example, just like our magnetic field. You know, when you have a magnet and you have an object, this is a magnet and there's an object, a magnetic material. Now, if I need this object to magnetize this material, the distance between this magnet and the magnetic substance, this material here, this distance between them is the magnetic field. The same thing is applicable in the case of gravitational field. The region of space where gravitational force is felt. For instance, these are two masses or two objects, and in between them, this space in between them is called the gravitational field. Gravitational field. Why? Because this object can experience a force of attraction. There's a force of attraction between two masses. So that leads me to the definition of gravitational force. So gravitational force is the force of attraction that exists between two objects on the Earth's surface or in the universe. Take note that I said the force of attraction. For instance, two bodies, let's say the Earth and the Sun. There is a force between them. And we said that force is a force of attraction. Force of attraction between them. And that force is what we call the gravitational force. This particular force is what makes it possible for planets to remain in their orbit. There's a force of attraction between the Earth and the planet, and that force of attraction is what we call gravitational force. So quickly, I'm going to talk about Newton's law of universal gravitation. Newton's law of universal gravitation. This law states that the force of attraction is directly proportional. You know, I told you that we always have force of attraction between every object on the surface of the Earth or in the universe. That there's always a force of attraction between two objects or between two bodies. So now, according to Newton's law of universal gravitation, it states that particular force that we're talking about here, that this force F, which is measured in Newton, that the force of attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance apart. Okay, so what that means mathematically I'm just going to take it now. I'm going to write a mathematical statement. It says that the force of attraction is directly proportional to the product of the masses. Take note, product of the masses. And inversely, force is directly proportional to product of the masses. That's, let's say the masses, and we have M1 and M2. So force is directly proportional to the product of the masses and inversely proportional to the square of the distance. This same force is inversely proportional to the square of the distance. Let's represent that as r squared. So this is what Newton's law of universal gravitation states. This is a mathematical representation of Newton's universal law of gravitation. Okay, so if I'm going to combine this, I can write it as F is directly proportional to M1 M2 over r squared. To remove this proportionality sign, I'm just going to introduce a constant. Now take note of this. So here is the mathematical statement. Mathematical statement of Newton's law of gravitation. Okay, so I'm going to define the terms here now. My F is the force, which is measured in Newton. The capital G is called the gravitational constant. It's called the gravitational constant. And it has a fixed value of 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram squared. So this is the constant. This is the value for the gravitational constant, capital G. Now my M1 and M2, they are the masses, or two bodies separated by a distance. They are the masses. Then R is the distance between these two masses. Is R. I can have M1 here and my M2 here. They are distance apart. The distance between this place to this place is what is denoted as R. So distance between the masses is my R, and is measured in meters. The masses are in kilograms. Okay, so I want to believe that is very, very explanatory. Okay, what Newton meant by this law is that the force is inversely proportional to the square of the distance. That means on the Earth's surface, from the center of the Earth, the farther you are away from the center of the Earth, the less the force of gravitation you experience. I don't know if you understand, because the same force is inversely proportional to the square of the distance. So the farther you have from the center of the Earth, the farther you have from the center of the Earth, the lower the force. So the force of attraction, actually the gravitational force decreases when you are farther away from the center of the Earth, and it increases when you are closer to the center of the Earth. And this is what actually happens in the case of rockets. In the case of rockets leaving the Earth's surface, once they leave the Earth's surface, because of the distance, their distance away from the center of the Earth, the force of gravity, or the gravitational force they experience is minute compared to what that object or the body would have experienced when it's still within the Earth's surfaces. Sorry, when it's still within the Earth's surface. Also, the force is directly proportional to the product of the masses. So that means at the center of the Earth, bodies experience a greater force of attraction. The closer you are and the more massive an object is, the closer it is also to the center of the Earth, the greater the force of attraction. I hope that is very explanatory. Likewise, the lower the force of attraction, then that means the less massive an object is. So the higher the mass, the higher the force of attraction between the two bodies. The higher the masses of the body, the higher the force of attraction between them, and the lower the. Okay, quickly, I would like us to solve a question on that using Newton's law of universal gravitation. So I have this question here. The gravitational force between two objects of masses 10 raised to the power 24 and 10 raised to the power 27. Of course, you know they will be in kg. So I'm just going to write mass M1 is equal to 10 raised to the power 24 kg, and then mass M2 is 10 raised to the power 27 kg. Take note of this. These are the two masses. And they said the gravitational force between them is 6.67. So they're giving us the force, which is F. The force F is equal to 6.67 Newton. And they're giving us capital G, which is 6.67 times 10 to the power minus 11 Newton meters. So what are we asked to find? Calculate the distance. The distance. Okay? So I'm just going to write out our formula, which is F is equal to GM1 M2 over R squared. So from the question, we have our F, which is this. We have G, which is this. M1, M2, we have F here, which is this already. But we don't have R. So we are actually calculating for R. So all I need to do is to make R the subject of the formula, which is the distance. I'm going to make R the subject of the formula. So in other cases, they can actually give you G, M, and R. They will ask you to find F. The formula is still applicable. At times they will give you F, R, G. They will ask you to find M. This same formula is applicable. All you need to do is to make whatever it is you're asked to find, make it the subject of the formula, like I'll be doing now. So I'm just going to cross multiply. So this is half R, FR squared is equals to GM1 M2. Remember, I want to make R the subject of formula. So I'll divide both sides by F. Sorry. F cancels F. So now my R now, I'm just going to find the square root of both sides. So I have my R. That means this is what I'm going to work with. Don't be confused, it's still the same formula. It's still this formula. All I did was, instead of making F the subject of formula, I made R the subject of the formula. So this is what I'm going to be using. My R, therefore, is equal to, wherever I see G, I'm just going to put it. This is my G. M1 is 10 raised to the power 24. M2 is 10 raised to the power 27. Everything all over F. My F here is 6.67. So by the time I multiply all of that and divide by 6.67, then take the square root, I have 1.0 times 10 raised to the power 20. Don't forget we said R is in meters. So back to the question, the distance between these two masses is 1 times 10 raised to the power 20 meters, which is the distance between the two masses. I want to believe that's very explanatory. Quickly, another concept we will be considering is the relationship between G and G. I mean relationship between capital G and small g. Okay? So capital G is the force exerted by the Earth on every object on the surface. That means every object on planet Earth experiences a force which we call capital G, which is the gravitational force. Okay? While small g is the acceleration due to gravity on a free-falling object. Already we have an established fact that every object on the Earth experiences a force. Fine, quite alright. But G now is peculiar to any free-falling object. What do I mean by that? G is responsible for the downward motion of any object that is being thrown upward. Like if I throw my marker up, it definitely come down, and that acceleration with which it comes down is called this acceleration due to gravity, small letter g. It is attributed to any falling object, any free falling object. They fall as a constant acceleration, which is, the value of this is 9.8 meters per second. The value of G is equal to 9.8 meters per second squared. So it has that. Now quickly, I would just like to clarify again the difference between capital G and small g. We learned earlier that the capital G is the gravitational constant, and that is given by 6.67 times 10 raised to the power minus 11 Newton meter squared per kilogram squared. While small g, on the other hand, is the acceleration due to gravity. It is experienced by every free falling object. Acceleration due to gravity. And the value is small g is equal to, we use 9.8 meters per second squared. But g varies. I mean the small letter g varies. Capital G is constant. It's fixed. The value is constant or fixed. That means anywhere in the world, capital G is 6.67 times 10 raised to the power minus 11. It doesn't change. But small letter g, on the other hand, it changes. It changes with altitude. Changes with altitude. That means it has no fixed value. That means it has no fixed value, which explains why at times you have your g is equals to 9.7 meter per second squared, or you have it as 10 meter per second squared, or you have it as 9.8 meter per second squared, or 9.9, and so on and so forth. That is simply because small letter g here changes with altitude. At the center of the earth, the small letter g is higher, is greater. But as we move away from the center of the earth, as we move up, it tends to be lower. But capital G, on the other hand, is fixed. The value is constant. And one more thing I would like to add to this is that for G, which is the capital G is a scalar quantity, while small g is a vector quantity. This is the third difference between them. And the last one I will be talking about is in terms of their unit. The unit of capital G is equals to Newton meter square per kilogram square, while small g is meter per second square. So very important, I would like us to take note of those differences. Okay, so in terms of formula, I'll quickly like to talk about the relationship between capital G and small g. Remember that F is equals to mg, and also, according to universal law of gravitation, F equals to g m over r squared. That's two masses, m1 and m2. So how do we relate this? From here, I'm going to make g the subject of formula. So from here, g is equals to f over m. I want to believe you understand how I did that. I made g the subject of formula. So that means g is equals to f. My f here is mm over r squared. I can write this as g is equals to f divided by m. So my f here, g is equals to, my f here is this. The whole of this is my f. So I'm just going to put it there. Divided by my m, divided by m. We know your mathematics. I'm just going to rewrite this as mm over r squared. By the time I change this division sign, it becomes 1 over m. So m cancels m. So I have small g is equals to gm over r squared. Since this has cancelled this already, and that gives me the relationship. So this is the formula connecting g and g. You can see that in this formula, we have both small letter g and capital G. So in case we are asked to establish the relationship between g and g, this is what is required of us. So we already know that g here is acceleration due to gravity. Our m is the mass. Our g is the gravitational constant. which is 6.67 times 10 raised to the power minus 11. G, we use 9.8 meters per second squared. And our R is the distance apart. The distance. So I want to believe this is very clear. From here, we may decide to establish a relationship by making M also the subject of formula. If we make M the subject of formula, this is what we are going to have. We have G R squared over G. And if we make M the subject of the formula, gravitational potential. This is the work done in moving a mass from infinity to the point. What that means is that, let's say this is the center of the Earth, and I have a mass somewhere here. The work done in moving this particular mass to this point is called the gravitational potential. The gravitational potential is the work done moving a unit mass from infinity, could be anywhere, to this particular point, and it's given as V is equals to minus Gm over R. While gravitational field intensity, on the other hand, is defined as force per unit mass, force over mass. That is I is equal to F over m. Force is measured in Newton, mass is in kilogram. So this is what we have. Gravitational field intensity. And here is the unit. So quickly, we are going to look at an example of that. The magnitude of the gravitational attraction between the Earth and a particle is 40 Newton. That's the force, so we are given the force to be 40 Newton. If the mass of the particle is 4 kg, M is 4 kg. We said calculate the magnitude of the gravitational field intensity. Gravitational field intensity. I. And you recall that our gravitational field intensity is equal to force over mass. So from here our force is 40. So we have 10. As our gravitational field intensity, which is 10 Newton per kilogram. 10 Newton per kilogram. So the gravitational field intensity is 10 Newton per kilogram. The second example here is this. It says, calculate the gravitational potential at a point on the Earth's surface. Radius of the Earth is given as 6.4 times 10 raised to the power 6 meters. The mass of the Earth is 6.0 times 10 raised to the power 24 kg. So we are asked to calculate the gravitational potential. You recall that our gravitational potential minus Gm over R. So this minus indicates that there is a decrease. So we are just going to ignore it while we are doing our calculations. And we know that our G is equal to 6.67 times 10 raised to the power minus 11 Newton meters squared per kilogram squared. So I'm just going to put that into equation. The mass is 6.4 times 10 to the power 24. Our R here is 6.4 times 10 to the power 6. So by the time I multiply this and divide, I'm going to have 6.3 times 10 to the power 7 joule per kilogram. That's the unit of the gravitational potential. So they said calculate the gravitational potential. So the gravitational potential at this particular point is equals to 6.7 times 10 raised to the power 7 joule per kilogram. I want to believe that is very true. Don't get me wrong, leaving the Earth's gravitational influence doesn't mean that there is no gravity out here, outside the Earth. There is, but the gravity in here is more than what you have. Escape velocity. This is the minimum velocity required for an object to escape the Earth's gravitational influence. That means for any object on the surface of the Earth to escape the influence of the Earth's gravitational force, a particular velocity is required, and that is what we call escape velocity. I'm going to give an analogy. Let's say this is the Earth. So for a particular object to come out of the Earth, it requires a particular velocity. And that minimum velocity, the least velocity required, is called the escape velocity. So at a particular velocity, an object is able to escape from the surface of the Earth. And the application of this is what we see in rocket propulsion. And when a rocket is being launched, it is launched at a velocity, which is called an escape velocity. For the rocket to successfully leave the Earth, that means it has attained or it possesses the minimum velocity required by anybody. So what happens in the case where an object is launched or a rocket is launched and then it falls back to the ground, while it hasn't even left the Earth, or while it's still within the Earth? In such cases, some is due to the fact that the velocity at which it's being launched is not up to the required velocity. So let's take note that we said escape velocity is the least or the minimum velocity required by a body to escape, to come out of the Earth, to actually escape the Earth's gravitational influence. So I'm just going to go ahead and show us how we arrive at the formula for escape velocity. So you recall that we said gravitational potential is the work done in moving a body from the center of the Earth to from infinity to the center of the Earth. So that means work done equals to, you remember. But in this case, we have two masses. And you also agree with me that this work done is the same thing as kinetic energy. How? Before you can move a body from that point to this particular point, that body will need to move. And we said that energy due to motion, or energy possessed by a body in motion. It's called kinetic energy. So we can actually say that work done in moving the body from infinity to this point is the same thing as kinetic energy of the body. So I'm just going to say this is kinetic energy. And you know that kinetic energy is given by half mv squared. So I'll just equate this to half mv squared. So if I cross multiply, I have 2g mv squared half. I'm trying to make v the subject of the formula here. So I have over mr. V is our escape velocity. m. So from here I have v squared is equals to 2gm over r. So if I take this up, my v will be square root of 2gm over r. And this gives us the formula for calculating the escape velocity. So our escape velocity, v. Our r is the radius, v is the escape velocity, g is the gravitational constant, and m is the mass. So we could use this formula or from, you recall that m is equals to gr squared over g. Do you remember this formula when I actually explained the relationship between capital G and small g? So from this formula, I'm just going to substitute this into the equation. So substitute into v is equals to square root of 2g, so this is my m, times m divided by r. G cancels g. So my v is equals to square root of 2g r squared over r. R cancels r, and that gives me v is equals to square root of 2g r. Or in the case where you have when you are given the mass, you could use this. So escape velocity is giving us this. And of course, it's measured in meter per second. So a quick example on that is this. A rocket is launched from the surface of the Earth. If the radius of the Earth is 6.4 times 10 raised to the power 6 meters, so we have our radius to be 6.4 times 10 raised to the power 6 meters, and the acceleration of free fall due to gravity is g, which is 10 meters per second. So the question says calculate the escape velocity, v. You recall we have vgr, and remember that we have this for escape velocity. V is equals to square root of 2gr, and we also have v is equals to 2gn over r. We don't have n, so we can't use this. 2gr, we have gr, so we can use this. So that means we are using this, we are not using this, based on our parameters. So v is equals to square root of 2 times 10 times 6.4 times 10 to the power minus 6, which will give me 1.28 times 10 to the power 8 meter per second. Our escape velocity is 1.28 times 10 to the power 8 meters per second. You can see it's very simple. Another concept we'll be looking at now is Kepler's laws. The first law states that the planet travel in an elliptical orbit with the sun at one focus. They travel in an elliptical orbit. I hope you know that when they say something is elliptical, it's something of this shape. So according to Kepler, it says that the planet travel in this orbit with the sun at one focus, not at the middle, at a particular focus. So according to them, the sun is either here or here at one focus, while the planets are traveling in this elliptical orbit, not even in a circular orbit, but in an elliptical orbit. Now the second law states that the line joining the sun and the planet sweeps out equal areas in equal time. The line joining the sun and the planet sweeps out equal area in equal time. What that means is that, let's say this is the sun and this is one of the planets. The line joining this, when it's this line, what I will have here, the distance from here to here will be the same distance if I take it from here to here, or if I take it from here to here, or if I take it this way. It seems like it should be shorter. What I will obtain here should be shorter compared to what I will obtain here. But according to this law, because of the elliptical orbit, it says that the line joining the sun and the planet sweeps out equal area in equal time. What are the distance from here to here? The same thing as the distance from here to here. The same thing as the area, the same distance from here to here, the same thing as from here to here, and it keeps going like that. While the third law states that the square of the period of revolution of the planet are proportional to the cubes. The square of the period is proportional to the cube. I don't know if you understand that. Proportional to the cube of their distances. And the third law states that the square of the period of revolution, the square of the period of revolution of the planet is proportional to the cube of the mean distances from the sun. What that implies is that the farther away, let's say this is, okay, we said with the sun at one focus, according to the first law, this is the sun. Let's say this is one of the planets, and this one is another planet here. Now, what this law tells us is that the period, the time taking, the period of revolution, the time taking for this planet to move round is proportional to its distance from the sun. The time taken for it to move is proportional to the distance away from the sun. So the farther the distance away from the sun, the more time it will require to go around the sun. That means this planet here requires more time to move around the sun compared to the planet here. That's because the distance, we said the period of revolution is proportional to the distance apart. The distance from here to here is more than the distance of this planet from here to here. So because of that increase in distance, it also explains why this planet will require more time to move around. Period, T is the period. T is equals to period, and R is the distance. The distance from here to here between the sun and the planet is the R. So that will be called Kepler's Law. So here are some exercises that I think we should attempt